Hi everyone, welcome to our webinar today. The topic for today's webinar is Nantucket Island Energy Storage, Batteries for Reducing Peak and Deferring Infrastructure Investment. This webinar is being presented by the DOE-OE Energy Storage Technology Advancement Partnership, also known as STAP. We'll talk more about that in a bit, and we'll also move on to our guest speakers in just a moment. But before that, I'd like to go over a few quick webinar logistics. You have a couple of options to join the audio portion of our webinar. You can call in via telephone or connect via computer mic and speakers. If you'd like to minimize the webinar console so that you can view the presentation full screen, you can click on the orange arrow that you see circled there. And you can also click on the arrow to expand the webinar console. One thing that you might like to do with your webinar console is to submit questions and comments. We would like to hear from you. We'll be saving some time for a Q&A with our audience following our presentations. So please type your questions and comments in as you think of them. Don't wait until the very end to submit your questions. And a final note, this webinar is being recorded. We will send you an email with a copy of the webinar recording and a PDF of the webinar slides, probably this afternoon, at least within 24 to 48 hours. And we'll also be posting those webinar materials on CISA's website at cisa.org/webinars. That's a good web address to know because that is where we list all of our upcoming webinars as well as where we post the webinar archives. So with that, I'm now going to turn it over to my colleague, Val Story. Val is a project director at the Clean Energy States Alliance, and she is going to get us started today. Val?
Hi, thank you, Sam. Thanks everyone for being here with us today. Welcome to today's webinar. So as Sam mentioned, today's webinar is being brought to you under our Energy Storage Technology Advancement Partnership Project, otherwise known as STAP. And this project is funded by the U.S. DOE Office of Electricity through a contract between CISA and Sandia National Laboratories, and it supports and facilitates energy storage development and deployment. Up on your screen, you can see a few examples of some large-scale projects that we have helped facilitate and develop through STAP. So one of STAP's key activities is the facilitation of public and private partnerships between DOE, the national labs, state agencies or municipal agencies, utilities, and even private partners to deploy large-scale energy storage projects such as the ones on the right side of the screen. We also disseminate information to stakeholders such as via today's webinar, and we support state energy storage efforts through technical, policy, and program assistance to develop programs and policies. Next slide. Thanks, Sam. So we definitely would like to give a big thank you to Dr. Imre Gyuk, who is actually with us today, one of our panelists, and will be speaking shortly. I'll tell you more about Dr. Gyuk in a moment, and also want to thank Dan Borneo, who is the Engineering Project and Program Lead at Sandia National Laboratory. Next slide. So I mentioned that the STAP project is co-managed by CISA, or the Clean Energy States Alliance, for whom I work. Just a quick introduction to CISA. We are a nonprofit based in Montpelier, Vermont, and we work with our members to advance clean energy. And our members are state energy offices and related agencies, and you can see all our members up on your screen. And we work with them to advance clean energy, including through financing strategies, the exchange of information, through partnership development, by offering technical assistance, and more. So with those brief introductions, let's move on to our panelists. Next slide. As I mentioned, our first guest speaker today is going to be Dr. Imre Gyuk at the DOE's Office of Electricity, who has provided co-funding for the analysis that Patrick Balducci at PNNL, Pacific Northwest National Lab, will be talking about later on today. Dr. Gyuk is first going to give us an overview of DOE's energy storage programs, and he's also going to give us a brief update on two grid-scale energy storage projects in Massachusetts, and then I'll do a few more intros and tell you more about the content that we are going to cover today. To tell you a little bit more about Dr. Gyuk, For the past 2 decades, he's been directing the Electrical Energy Storage Research Program in the Office of Electricity, where he's developed a wide portfolio of storage technologies for a broad spectrum of applications. He has supervised the 185 million ERA stimulus funding for grid-scale energy storage demonstrations and is now partnering with states on numerous storage projects for grid resilience. He has a BS from Fordham University, and he received his PhD in theoretical particle physics from Purdue University. Dr. Gyuk, thanks for being with us today.
Hi there. Here we are. Well, today we are going to talk about energy storage and about projects in Massachusetts. Massachusetts has become rather a hotbed of energy storage activity in recent years. In particular, the legislature has taken on a number of important activities. First of all, they have developed a target for 2020 of 200 megawatts. Well, that's upon us. And pretty soon, 2025, this will be 100 megawatts. So a fairly decent target for a relatively small state. They have also, in HB 2496, said that storage is a green energy technology. This means that storage will be considered when buildings are participating in green energy programs. H 4857 directs the Massachusetts Department of Energy Resources to develop proper valuation of energy storage for planning purposes. That's very important because this is looking forward towards the future. And the state is not only directing things, it is also providing specific funding and monetary resources. More than $200 million in grants for 26 projects. Besides that, of course, Massachusetts also has a considerable amount of research in its universities and a fair number of companies involved in the energy storage business. My forward isn't working. There we are. So, Massachusetts has quite a few projects that they are funding. And of course, the DOE Office of Electricity Storage Program is building and validating business cases through innovative pilot projects, such as the ones that are being funded in Massachusetts, particularly with respect to resilience, sustainability, and grid stability. Now, we work with national laboratories, notably Sandia and Pacific Northwest Laboratory, and they have developed for us tools for valuation. And the valuation is essential if you're going to have meaningful projects and if you're going to look both forward and backward in terms of having a business case. At Sandia, we have the Quest tool, which works particularly well for deregulated utilities where you have a market structure in place. This is, of course, the case for Massachusetts. At Pacific Northwest Laboratory, we have the BSET tool, Battery Storage Evaluation tool, that is particularly suitable for vertically integrated utilities. However, it also works for market structures. So you're going to get examples of both of those at work here in Massachusetts. The first one is one that by now is a classic, and that is the project in Sterling, Massachusetts. They received a grant from the Massachusetts Community Clean Energy Resiliency Initiative, which originally intended to provide resilience for the police station dispatch center. We got in touch with them early on, and we offered to model the system. And after that, we suggested that they might want to extend the system into 2 megawatts, 2 hours, and create a business case which actually creates a return on investment. And they went along with that. The groundbreaking was in October 2016, and 3 months later, the energy storage facility was already constructed. The annual savings, and here is an entire year of annual savings, bore out the model calculations completely. And this is what it looked like over a longer time scale. You see the monthly peaks going on, saving in demand charges, and then the yearly peak and the monthly peaks again, the yearly peaks, the monthly peaks. So once you have this set up, benefits keep accruing. And in fact, over a 2.5-year period, this project allowed the municipal department utility to save $1 million in avoided cost. And the small utility gained considerable fame on the international scene for doing a project well. Here's another project, also starting with a grant from Massachusetts. And here, Pacific Northwest Laboratory took on the job of trying to find out how to unite 3 particular facilities into a microgrid and tie together multiple grid assets to improve resiliency. So there is PV, there's diesel, there's biomass, and then to tie those together, 441 kilowatts of new energy storage for 1 hour. The total 20-year benefits turned out to be about $2.5 million at a cost of $2.2 million. And the return on investment is 1.16, which is not bad at all. In the diagram, you can see the costs and the benefits. And the benefits come from a whole lot of different sources, like demand charge reduction, outage mitigation, PV energy payment reduction, and others. Altogether, it turned out to be a valuable proposition. And of course, you're going to hear mainly about the Nantucket case, which was also done by Pacific Northwest Laboratory for the analysis, and was equally productive. But here's something to think about. Energy storage value depends highly on local regulatory structure. The problem is that this structure may change in time. It may change both for the better for the project or for the worse. So projects may turn out to be less productive than they were intended to be, or they may have higher return. With this thought, I will leave you.
Thank you, Imre. Thanks for kicking things off for us and introducing the various benefits of energy storage based on different use cases and introducing us to some of the projects in Massachusetts. Now on to the next Massachusetts project we're going to talk about today. So we're pleased to have two guest presenters with us to talk about Nantucket Island's new battery energy storage system, which was installed in the summer of 2019. And we're also going to be covering the modeling analysis performed by PNNL that evaluated the technical and financial benefits of installing that storage solution. We're first going to hear from David Bianco of National Grid, and he's going to cover the reliability and technical aspects of the project and give you an overview of how National Grid is operating its system on the island and the battery's role in peak shaving. And then we're going to hear from Patrick Balducci at PNNL, who's going to discuss their modeling of the system with the combustion turbine generator and the battery energy storage system. And Patrick's presentation is going to cover both the monetary and the non-market benefits of the system. Let me introduce David Bianco now, and let me also remind our audience to please type in questions into the question dialog box. At the end of the presentations, we're going to host a Q&A session. So I encourage you to type your questions as they come up rather than waiting until the very last minute. So David Bianco is a principal engineer at National Grid, where he has worked on distribution planning, power generation, power supply, and substation engineering. His interests include battery energy storage solutions with a focus on control system, co-optimization of reliability, and markets. David, thanks for being here and welcome.
Greetings, thank you. My name is David Bianco, and I'm here to review a storage installation in a remote area off the coast of Massachusetts called Nantucket Island. National Grid has installed storage in various locations around its system. This map gives some more detail on that. The one we're focused on today is the one on the right-hand side in blue lettering, Nantucket Battery as a transmission solution that's 6 megawatts, 48 megawatt hours in rating. Nantucket Island itself, you can see on the right-hand side is a little blue island, and that's the island. It's 26 miles off the coast of Cape Cod. It is fed via 2 undersea cables and has about 12,000 customers, year-round customers. It is a summer peaking area, tourism area that peaks to around 50,000 people during the summer. Prior to this battery energy storage project, the island has had existing oil-fired combustion turbines for lack of supply in an emergency when an emergency arises. Again, as I mentioned, it is a summer peaking area and it is limited by equipment ratings. When we started this project, we was facing some fairly high load percent increases in load growth, as you can see on this slide, and we also projected forward as shown for study purposes. The issue that we're solving was an N-1 condition, whereas as you can see in the photo, there's 2 cables to the island. If one undersea cable fails during the peak, the remaining cable would become overloaded. The ultimate solution we chose was upgrading the existing diesel combustion turbine generator and installing a new battery energy storage system in combination. From a value perspective, which will be talked about more later, it did defer the investment of additional undersea cables and allows us to pilot market participation in ISO New England. Storage in general as a non-wires alternative, just in a very general sense, it's important to understand the techno-economics of different energy storage applications, compare energy storage against conventional distribution and transmission solutions, and recognize economics as a key decision variable. considerations as we went into this project. Obviously the N-1, as I mentioned, but also we had a series of interconnection studies, both local and at the ISO level. We had to think about how we coordinated the control of assets on the island and balancing the reliability need and market need. We had, utility ownership is the model that this is under. National Grid owns the asset, and the availability of land on a small island was also a consideration. With this hybrid option that we chose with both the combustion turbine generator and battery, it defers the need for that cable, avoids that expense of that extra cable, and provides the contingency relief during a loss of supply, with side benefits of T&D benefits of operating the local grid for power quality, voltage, power factor, and other ancillary type services, and yields a efficient, environmentally sustainable solution that's very effective. The DOE did support us during this project. As shown here, Pacific Northwest National Labs supported various economic and technical studies. And again, this will be talked about further later, but this is a real high-level summary and shows the path if you like to read the report. During the selection process, some of the differentiators, when we went out looking at suppliers, and these were some of the key areas that become part of that evaluation in case anybody is embarking on one of these projects. We did go out to the marketplace with technology neutral. We were, trying to keep in mind what we had for footprint, configuration, whether it's indoor or outdoor facilities for the battery. We had to pre-qualify suppliers. One of the big differences with this project is logistics and the remote nature of it, being off the coast. So contractors' abilities to handle that was certainly a consideration. Technical and commercial term, schedule, site issues, all of these were factors in the discussion. During the preliminary engineering process, not only did we have the interconnection studies, but it was a fairly weak system from a power system perspective off the coast as far as it is. We had to be concerned with these large DERs we were putting in on a small island and how they controlled each other, and coordinated control of other devices already on the network, whether they be LTCs, line caps, voltage regulators, etc., and be considerate of what happens when we operate the CTG, combustion turbine generator, and the battery system in parallel, and avoid any system violations. Inverter modeling is a challenge during this time period, and balancing again those reliability and market needs, and peak shaving as a goal, and designing the system to be able to predict weather and local and grid considerations. It was a fairly sizable project on a small area, so we had to have a pretty complex project execution strategy. We actually had three contracts. The area on the left represents the first contract for what we call balance of plant to get the site ready. Contract 2 was for the combustion turbine generator, and contract 3 was for the battery energy storage. Each of those three contracts went through an engineering phase, a procurement phase, and a construction phase. And balancing these was quite challenging. Construction logistics. Again, on an island, labor, how you resource labor on an island and how you lodge people on an island is a whole area unto itself. On island and off island equipment availability, staging equipment on the mainland, and ferry coordination to get equipment over and back. Weather that affects ferry availability, and progressing with the construction work, and even having a laydown area was challenging to work through. So a lot of logistics. Commissioning wise, should anyone be in the future commissioning one of these systems? I think the ownership and delivery model really drives your approach, whether who owns it and how it's getting delivered and how it's all contracted. But starting with commissioning and acceptance in mind is really key, right? So speccing the system properly with that commissioning acceptance in mind will pay off in the long run. We did utilize EPRI and Electric Storage Integration Council and IEEE as some guidance and background in all this. It can take, a short, depending upon the actual item commissioning task, can take a day, can take a month. It's obviously everyone's systems project might be different, but it does take longer than anticipated. Testing one of these systems too, depending upon where it might be geographically located, what you have for supply and load available to be able to test the system, whether you're bringing in your own generation to test it, and load banks for load, all things to think about and strategize. But going through this does baseline and alleviate later operational problems since you have that foundational data at startup. It also helps train personnel and ensures a safe and operational system. The challenges that we had was developing comprehensive technical and contracting specs. If you remember back to the org structure chart there, forming a project delivery structure that worked for everyone, supplier, the utility, etc. And of course, trying to be efficient by paralleling tasks, design, procurement, construction, and testing, and coordinating with a wide degree of stakeholders. New technology integration during engineering, construction, and commissioning can always be add that extra layer of challenge. And again, the large equipment and logistics. This was a hybrid installation, so that was another layer of complexity. Industry models need to be better matured with PSSE, SIME, Aspen. Some of these engineering tools that we use need upgrades to model DER appropriately. Remote IT monitoring and requirements for the suppliers of this equipment is a big coordination point, and takes a lot of work. And then they ultimately those IT monitoring help drive favorable maintenance and warranty needs. Our contract for the battery storage system is a 20-year contract with augmentation along the way. Final thoughts. Islands, because they're remote, cause unusual and unique needs. Peak seasonal demand does create supply risk, and sequencing of major suppliers and balance of plant adds to an already complex scenario in a remote area. But remote radial lines do create an application for storage to satisfy reliability. So if you are looking at something in your area and you do have a remote radial, then it's probably a good application for storage. And National Grid, as a result of all this, has deferred the need to build a third undersea cable. And I think at the end, we're going to take some questions, but that's all I have for right now.
Great, terrific. Thank you, David, and thanks to everyone for already typing in lots of great questions. Keep them coming. We're going to move on to Patrick Balducci's presentation now. Let me introduce Patrick Balducci, the Chief Economist at PNNL, where he has 25 years of professional experience as an economist and a project manager. He's been there since 2001, and he's currently leading the industry acceptance area of the PNNL energy storage program and has extensive experience in modeling the benefits of energy infrastructure and in leading research and development efforts supporting the U.S. So Patrick is going to take us through, like I said, both the monetary and non-monetary benefits of the system and talk about the modeling of Nantucket Island's energy system. Patrick, thanks for being here.
Yes, thank you. First of all, can everyone hear me? Loud and clear, I
Yes.
hope. Great, thank you. So, yeah, I'm currently the chief economist at Pacific Northwest National Laboratory, at least for the next 10 days. Then I'm actually moving to Argonne National Laboratory, where I'll be the group manager for the Power Systems and Markets Research Group. So a shout out to my PNNL and Argonne colleagues. So I also want to highlight the team that I've led for the past 8 years roughly, comprised of physicists, engineers, and economists, several of whom are listed below there in terms of other contributing authors. They all made a significant contribution to this effort. I really want to recognize those efforts. So the project overview, typically I present this project in isolation, but thanks to David and his exceptional presentation, that really is beneficial from my perspective because I don't have to dig into the project as much. So I won't get into this too much, but yeah, the background was that National Grid came to us at Pacific Northwest National Laboratory. They recognized the significance of the deferral opportunity. As you can see there, small resident population that swells during the summer months. So it was really only 200 to 300 hours out of the year where you were going to be entering that N-1 contingency window. That really offered a unique opportunity for energy storage. Rather than adding that third line that would actually wrap around the island and then connect at the Bunker Road substation there at a very high cost of $150 to $200 million. The question was, could energy storage be used to defer that investment? And National Grid answered that question. But then their question to us at PNNL is, what else could it do? Since it's only operating a few hundred hours out of the year, what could you do with the other 8,400 odd hours out of the year? And so that's what we help them with. So using the temperature dependent CTG with a maximum capacity of 16 megawatts and a 6 megawatt, 48 megawatt hour Tesla lithium ion battery system. The first thing I can tell you is that we had a great team working together here, and you can see we were really performing three main functions. First of all, we built a model to simulate operation of their distribution system. We took the SIME data, placed it into GridLab-D and OpenDSS. We performed an economic evaluation, so simulating operation of the battery system for a 1 year period, and then defining value over the 20-year economic life of the systems. And then finally, we also aided in the development of control algorithms to aid National Grid in moving forward and actually capturing these values in real time. I can tell you that through the generosity and leadership of Dr. Imre Gyuk, we have some additional funding moving forward, or PNNL does, to continue on the assisting of National Grid in the development of these control systems, and also in actually estimating the value of the economic operations of the energy storage system moving forward. So not only did we estimate the achievable economic benefits over the economic life of the unit, but PNNL will actually be measuring those benefits over time to try to make it as real and instructive as possible. So the team was comprised of U.S. Department of Energy providing leadership and co-funding. This was 50-50 funding from the utility and Dr. Gyuk's group there at DOE Office of Electricity. And then we also had a subcontract with a PhD student there at Virginia Tech who was an exceptional distribution system modeler. Okay, so the economic use cases, we break them out into two categories: non-market operations, which really drive the analysis, but then also market operations. So non-market operations, the transmission deferral value is the most significant easily, but in addition, significant reliability challenges on Nantucket Island with the energy storage system and the CTG being used to address those outages. So using Lawrence Berkeley National Laboratory interruption cost statistics and the simulation of the outages, we could define the value in terms of value of lost load to those customers. Also, conservation voltage reduction, volt-var optimization, so improving the efficiency the provision of electricity on that island. And then in terms of market operations, forward capacity market, arbitrage, frequency regulation, and spinning reserves. And there are a couple images of the Tesla battery system, which we acquired from the Tesla website. All right, distribution system integration. What was really interesting about the work that we did here was, with many of these energy storage system evaluations, you're theorizing about the outage mitigation potential, and you take it as a given that you have the ability to actually operate the energy storage system or the microgrid or the energy storage system plus, combustion turbine generators or whatever combination of assets without consideration of the distribution system limitations. We recognize that there are distribution system limitations and that energy storage systems and combustion turbine generators don't operate in isolation. And so therefore you have to account for the limitations of the distribution system and also the opportunities in terms of outage mitigation. And so we could actually simulate each outage very realistically. So what portion of the island could be islanded and then outage mitigated when they strike. And then in addition, we identified locations. We could make recommendations with respect to investments. So for example, we found that you could not fully export the energy of the CTG plus the battery system in some circumstances without making more investments in terms of reconductoring lines in 4 locations on the island. We also showed that through advanced meter switching, not meter switching, but advanced switching, you could, feeder switching, you could actually really reduce the outage times, bring it down from a 1 hour lag before addressing the outage through manual switching to as limited as 1 minute or 5 minutes. And we could define the value associated with that and the cost. So you could determine whether or not the investment made sense. Okay, so non-market transmission deferral. As you can see here, we conducted a fairly sophisticated load analysis. So we obtained hourly load for 2019. You can see the lines there that show combinations. So if for just one cable or the cable plus the combustion turbine generator plus the battery storage system, or the cable plus the combustion turbine generator. So what this is showing is that if those peak hours exceed that gray line there, effectively you're now, well, if it exceeds the orange line, horizontal line there, you're in the N-1 contingency window. If you exceed that gray line, you're in it even with consideration of the combustion turbine generator. And then the orange squiggly line on top effectively shows you the entire system. It is variable because it's temperature dependent. So we varied the productive capacity of the combustion turbine generator based on temperature. So effectively each temperature throughout the year changes the capacity of that CTG unit there. And then of course we take those peak hours and then project them into the future. And this was actually a 95% sort of extreme, scenario. And what we showed is that you could get about 13 years of deferral benefits. And so you have a pro forma for the cable, projecting the full rate impacts over its economic life. And then in present value terms, that actually saves you more than $100 million in benefits. So this is a function of utility economics. You're building in all the costs associated with everything from insurance to taxes to returns to investors. And so this is a huge benefit from the perspective of the ratepayers of Nantucket, of National Grid in Massachusetts. Okay, so outage mitigation. We acquired historic outage statistics for the island and data. So all 704 outages over 11 years. You can see that it averaged 64 outages annually. We eliminated most of those outages, so we were actually under 100 over that 11-year period because many of the outages could not have been addressed through the CTG plus energy storage system operating in isolation. And then for the remaining outages, we created a statistically average outage year and then simulated those outages in our distribution model. And so what we could show is the with and without energy storage system and CTG scenarios, and then monetize those values by taking the affected customers. So we had customer statistics, residential, small commercial and industrial, and large commercial and industrial customers affected by these outages. And as you can see here, a really, significant benefit stream here. The annual value in terms of lost load under a variety of scenarios varied from $783,000 to over $1 million. So you can see with and without reconductoring, and with and without the automated feeder switching. So with those investments, you're picking up an additional, $250,000 in annual benefits. In addition to that, we simulated market operations. And so with respect to energy arbitrage here, we can see that we modeled the battery storage system, and only the battery storage system, not the combustion turbine generator, as a continuous storage facility, which was a new asset class for ISO New England, which is improving its market and removing barriers for energy storage systems, bidding it in to the market. And so what we were doing with our energy arbitrage here was we were using a little bit of a more sophisticated approach in the sense that we weren't assuming perfect foreknowledge. Oftentimes these economic assessments assume perfect foreknowledge with respect to prices. So what is done is historic price data will be used and embedded in the model, and then the model has perfect foresight into those prices and then bids in accordingly so as to maximize the economic return associated with providing arbitrage, so buying low and selling high in the ISO regional market. We didn't assume that. We used a combined statistical approach using the gradient boosting machine method and ARIMA. So basically, we were predicting prices based on historic trends and forecast temperatures on the island, and then bidding accordingly. And what that shows you is that particularly with the real-time market, you obtained more revenue than in the day-ahead market. However, the difference between the various bidding strategies actually drove the outcome fairly significantly. So if you assume perfect foreknowledge, you're going to estimate far more revenue than would be realistic. In addition, you can see that with the day-ahead market being the basis of predicting real-time market, you actually obtained the most revenue, so that it actually beat our statistically based model in terms of the revenue. And the reason was the statistically based model actually did better from a statistical perspective, so it was more effective at estimating the prices for the next day, but it failed to identify some very high price hours. So when you monetize the values, the day ahead market prices, which actually do account for things like supply side constraints that our model may not actually pick up using the statistical procedures, we actually obtained more revenue that way. Now, it's important to note that there were fairly significant cycling limitations, only about 150 cycles per year. And once you build that in, it actually eliminated arbitrage as a value stream. So with this battery system, a 48 megawatt hour system, you couldn't provide more than 7,200 megawatt hours of energy on an annual basis. So frequency regulation, this was the high value item. So there's three components to this. There's a capacity component. So you can bid in the full range of the capacity of the unit. So a generator, effectively, you're taking a midpoint and you're cycling up and down around that midpoint. But an energy storage system can provide at least twice the regulation capacity, because you have full regulation up and full regulation down, because you can be either charging or discharging the battery system. Also, they offer through the ISO New England market the ability to follow an energy neutral regulation signal, which is also quite beneficial. And you can bias your bid in such a way that you actually would have more charging than discharging. So what's great about that is that you're maintaining your state of charge while providing the service. Also, you're paid for mileage. So for all the energy that flows into and out of the energy storage system, there's a price for that as well. And then the final component is a performance-based score. And energy storage systems rate very highly, as you can see here, around 95% typically. If you can't follow the signal, then effectively the value of your asset is derated. Excuse me. And the energy storage system, there's not much duration because it's very effective at following that signal. And what's great about this continuous storage facility is you can simultaneously be providing multiple services. You can be providing arbitrage, frequency regulation, and spinning reserves. And you can see the three of those combined signals creating that very sort of unusual line to the lower right there, that sort of a combined signal that takes into account all three opportunities. ISO New England forward capacity market was trading at just $11 per kilowatt per month recently. Since then, it's effectively crashed. And going out to 2023, 2024, the market price is $2 per kilowatt per month. And so it's come down quite significantly. And in addition, you're bidding 3 to 4 years in advance, and you have to demonstrate, you have to effectively provide a notice of interest to actually participate in the forward capacity market. And so with this value stream, we were waiting several years to actually enter the market, and then taking advantage of much lower values than are evident in the marketplace today. And we built in all the historic market calls into our model so that we could co-optimize. So we don't assume the ability to provide all services simultaneously. Effectively, what we're always doing is providing bundled services. And so you can see here, we're addressing the multidimensional co-optimization challenges. I mean, effectively, if you're using energy in 1 hour, there's less of it available in the next, because energy storage systems are energy limited. And then in addition to that, you cannot simultaneously provide all services to the full extent of the battery system's capability. There's going to be technical limitations and limitations in terms of power and energy. And we built all that into this evaluation. Now, when you put all these values together, we see just the local services are providing a return on investment ratio of about 1.3. So, when you're obtaining about $10 million in outage mitigation benefits, and you add that to the roughly $110 million of transmission deferral benefits, and of course, these are all avoided costs, either avoided costs to National Grid, the utility, which it can pass on to its customers, or avoided costs directly to the customers in terms of value of lost load. But then in addition to that, we estimate significant additional market-based revenue that drives the return on investment ratio to 1.55. And the majority of those benefits are tied to regulation services. You can see about $18.8 million over the economic life of the system as presented in terms of present value benefits. So some really significant benefits there. So what we have concluded is that National Grid's decision to avoid the installation of the third cable and deploy the CTG and battery storage system instead appears to be a sound one. So you can see the local, just considering local benefits at 122 million generates a return on investment ratio of 1.3. Adding in the market benefits raises the return on investment ratio to 1.55. All the market rules and the load patterns suggest these are feasible and obtainable cost avoidance and market revenue. We realize that there are challenges in terms of avoiding double counting of benefits, and so National Grid would have to seek and obtain FERC approval to simultaneously provide these localized benefits and bid into the market marketplace. And to the extent that the revenues were generated, it would not be brought back to the benefit of the utility, but rather passed along to the customers that paid for the asset. And this is something that was recently encouraged through a FERC memorandum. And then finally, we have this distribution system model that's allowed us to really zero in on the volt-VAR and CVR and outage mitigation benefits. And we've demonstrated that if all the investments were made and the energy storage system in CTG, they were operated optimally, you could avoid on the island up to 46% of the customer minutes of interruption. So that's a significant resiliency benefit. Now, we did estimate that in terms of value of lost load to those customers, but of course that doesn't include all the benefits associated with the resiliency associated with not only the direct cost to those customers, but indirect and other costs, induced effects as those savings cascade throughout the economy. These could be fairly significant benefits that were not included in this evaluation. So we've got a final report that's been issued. We've got a working distribution system network model that we've turned over to National Grid to continue evaluating and exploring options for this project. We've published 2 study elements tied to the control systems. We have 3 more on the horizon, 1 tied to the economic assessment and 2 associated with the distribution system modeling work. And then Dr. Gyuk's program is funding PNNL to continue with the development of real-time control systems, or at least provide advisory services around that, and then monitoring economic operations in the coming years. And you can see the ribbon cutting ceremony there. There's Dr. Gyuk on the left-hand side, and I'm on the right-hand side. And for some reason, David Bianco isn't in the picture here. Turan Hill, which is the gentleman holding the tape to the right, was a leader on the National Grid side. So I really want to recognize the assistance that we received from National Grid, and there's a long list of the folks who are helping us on that side of the equation. And then finally, Dr. Imre Gyuk, his leadership and funding of this and all the efforts that really enabled the development of the methods and the models and tools that were brought to bear on this project were key. So thanks to all of those individuals. I would say you can reach out to me at these places, but that won't be true for very much longer. So you see my cell phone there, the 503 number. Please feel free to call, reach out if you have any more questions or have follow-on things you'd like to discuss. So I'll turn it back over to the moderator. Thank you.
Terrific. Thank you, Patrick. We've got about 8 minutes left for some Q&A. And Patrick, while you're still unmuted, let me ask you a question that has come up multiple times in the chat box. How can others, utilities, etc., work with PNNL on modeling of their system?
Great. So that's a great question. So the way this has worked in the past is that, and so it's going to be, once again, I'm leaving PNNL. So you can either reach out to the staff at PNNL. Dr. Vince Sprinkle would be a good person to speak with. You'd have to look up his contact information, or you can reach out to me and I can pass you through, or you can contact me directly and we can discuss, options for working together in the future. The way it has worked in the past is that, PNNL is funded through Dr. Gyuk's program. Sometimes there's grant funding as well obtained through states, and utilities often provide co-funding. But if you reach out to me or Dr. Sprinkle, then we typically reach out to Dr. Gyuk and DOE and try to find sources of funding. Co-funding, once again, is appreciated, and then we find the funding to work together. And I think the way Dr. Gyuk's program was really structured, and that's exactly how it worked with National Grid. They just reached out to us. They came out to Richland, and we had a series of meetings, all-day meetings, and so you work together and you find the funding. And Dr. Gyuk's program is typically targeting innovative projects. So there's there are limited resources, and you try to target something that's going to be propelling in terms of the industry. But if it's an interesting project, reach out to me or Dr. Sprinkle, and we work together to try to find the funding and do the work.
Terrific, thank you. All right, let's dive into some of the details on this battery energy storage system. So a couple of questions on the battery itself. How is it charged? Is it charged from the combustion turbine generator or the grid? How often is it charged? And how often has it been used to solve this N1 contingency, if at all?
That's for me, I assume.
Yes.
Yeah.
I think so, David.
Yeah. So it's charged through the grid, through the local distribution system. The CTG is not operated on a regular basis unless there's an N-1 or some emergency need. So it is charged from the grid, and we have not had since the time that the battery's been installed, we have not had that particular contingency occur.
Yeah, and I would add to that there was a little additional level of sophistication to our analysis, in the sense that folks would ask me the question of like, oh, so you're going to push energy back across those submarine transmission cables back to the mainland, right, when you're operating in the market? And of course, that's not how it works. It's effectively a load modifier. So there always has to be enough load to modify in order to participate in the markets. And so we evaluated load and did analysis that way to ensure there was always sufficient load. So that is to say, effectively, you're just reducing load on the island, and that's how the market would recognize you. In terms of, and there's telemetry effectively monitoring the operation of the battery system.
Great, thank you. And perhaps you both can address this next question. I'm not sure if it came up in the modeling or if this was a national grid decision, but how did you choose to install the CTG? I'm assuming that is a new installation, and if it was, did you consider renewables like solar and wind or other renewable technologies in place of the combustion turbine generator?
We did look at various alternatives. In fact, 2 CTGs or battery only, and we ended up going with the hybrid option based on the operational considerations and value that we got out of the hybrid scenario.
Great.
I've gotten that question. I've got
a great many. Sorry, do you want to talk?
No, please, Dr. Gyuk, go ahead.
Okay, I just wanted to say that a great many projects, in fact, the majority of projects of that type are solar plus storage. There are most of the solar projects that go on in places like California are now in conjunction with solar. So it's something that occurs quite frequently. It just wasn't particularly advantageous on Nantucket Island.
Especially given the footprint constraints as well.
Exactly.
Got it.
David, yeah, that's exactly what I was about to add. Okay. So David covered it.
Perfect. Okay. Let's talk about some island specifics. David, was there any local opposition to installing a grid-scale battery energy storage solution? Did you have to do a lot of public outreach? How did islanders look upon this proposed project?
I was not directly involved in a lot of that outreach. However, I from what I understand, it was very welcomed and actually encouraged. So it was looked upon very favorably by the local community, and as far as I know, they're happy with it to this day. But I don't have all the details on that. There wasn't significant opposition. There wasn't significant opposition to it. Go ahead.
I can add something to that. In general, it's very important to do public relations, to have the local community, whether it's municipal or state or whatever, on your side, which also means that you have to talk to the local building inspectors, fire chiefs. They should all be on board and be well aware of the projects and be working with the project. If you do that, generally, you will get good support for storage projects.
Thank you. We have reached the top of the hour, so I'm just going to ask one more question, and this one is for both Imre, Dr. Gyuk, and Patrick. Are there any tools that utilities and states can use on their own? Imre, I believe that you mentioned one in your introductory slides, but Patrick, any tools developed on your end as well?
Both the tools that I mentioned, the PNNL tool and the Sandia tool, are available for free. They're open to the public. Generally, you might want to have some help from the labs in how to use them, but they're available to anyone.
Great,
yes, and I will add to that two other tools of note are NREL's National Renewable Energy Laboratories REOPT tool, and also EPRI's storage vet tool. And I recently delivered a presentation that evaluated the relative strengths, weaknesses, and differences between those four tools, adding in BSET from PNNL and Quest from Sandia. And I will be at this PNNL address for the next 10 days. So if people want to reach out to me, either calling me or sending me an email, I'd be happy to share that presentation and answer any questions that folks have.
Terrific, thank you. And for those of you in the audience who weren't with us at the start of the call, all of these slides will be available on our website, as will Imre's slides that he shared and he links to, and has the Sandia and the PNNL tool he mentioned linked on his slides. So with that, I would like to thank our speakers once again and thank everyone for listening in. I'd also like to tell you about some upcoming webinars, which are on the next slide. Here are some upcoming webinars: Financing Resilient Power in Underserved Communities, Tuesday, October 20th. Cost and Benefits of Offshore Wind Transmission Options on Friday, October 23rd, and a webinar on carbon taxation on Wednesday, November 18th. Sam, sorry, apologies. If you could go back one slide, there's contact info for many of the speakers up on your slide. As Patrick mentioned, you can also reach out to him. His contact info is at the end of his presentation, and feel free to reach out to myself and my colleague Todd Olinsky-Paul with any technical assistance questions or any programmatic questions. Thanks everyone for listening, and have a great afternoon.
Bye-bye.
Bye.
Bye-bye.